Hello there, students, and welcome to part 2 of the lecture where we're looking at electron structure. So we just get right into it. So I told us we're going to continue, and we're going to continue from electron arrangements in monatomic ions. Remember from the last lecture we talked about monoatomic ions. We said they can be cations or they can be anions, but the singular fact remains that monoatomic ions are just one ions. So you have examples like sodium ion, which is a monoatomic cation, and then you have the chlorine ion, which is a monoatomic anion. So please don't forget, say the cation, anions, and an negatives. So in forming monatomic ion, electrons are removed from cations or added to the anion sublevels in the highest principal energy level. So remember we said the cations removal, anions addition. The same implies, because the sodium ion gives one electron and then the chlorine takes. So sodium gives, chlorine takes, and it's all there. So cations of group 1 forms 1 ions. Cations of group 2, like that. The same thing with the S and the P and all of those things we talked about. So elements of the oxygen family in group 16 form -2, then halogens -1 ions. So it's very hands-on and practical. So we see the noble gases, and then we see the other ions that we have here. So you have lithium, you see the +1s, you have the other group 2, beryllium, magnesium, see the +2s, and then you have some transition metals here, so you see them here, and then you have the others in the negative, and then you have your noble gases. So hence the whole idea of the configuration is so that you have the structure put into consideration, the ions as well. So the transition metal cations usually do not form ions from noble gas configuration. So the cations do form with charge ranging from +1 to higher numbers. So the outer exchange electron is lost before the d electrons. This is the first level. So remember I told us previously when we talked about the exceptions, we say the 4s is actually lesser in energy than the 3d, hence it can be bullied to give electrons on the basis of stability. Stability is everything with these compounds, with these atoms, because because even we as human beings, we're trying to be stable, and we can give anything to be stable. Sometimes we can even risk our lives for stability. Electrons or atoms do the same. So you have an example of manganese in this place, and you see it's normal as such. When you have +2, notice that there's no 4s2. Same thing applied when we're doing the nuclear symbol of Na+, where there's a +2, which is indicative of a removal of the 2 electrons on the 4s orbital. I hope it makes sense, but understand that normally when you're writing manganese, 25. Know that argon is 18, 19, 20, 25. Notice that once you're writing manganese, you include the 4s2 and 3d5. But when you now put a +2, you have to take out this 4s2 because now there's a charge to it. Because you can add. You can say, okay, 3d5, 7. No. It's the 2 on the 4s that has to go away for this. So we go further. So give the electronic configuration of ion 2 and bromine ion. So you have this, and remember we said for this you remove, for this you add. Let's just go to it. So the electronic configuration is this. So the cation of with +2 charge, you subtract 2 electrons. So in ion, you just take this out, and what it will simply be is taking the 2 electrons from this. You have the situation where the 4s orbital is no longer present. Simply put, we saw that from the previous. And then in this situation, you have your P 4p6. So notice that when you add one more electron, it completes it and becomes it's 4p5, it completes it and becomes 6 in this case, because we said for negative you are adding, for positive you are subtracting, because you're doing the reverse of what it implies. So you notice that with p6 it has attained stability, because that's the goal on both sides. So we now go to the periodic trend, and it's like trend. It's like when something is trendy, it means that it's what is reigning or what's available now. So when you're talking about periodic trends, it's almost like what the direction is on a periodic table. What's the direction? What's the focus on the periodic table? So you have chemical and physical properties of the element are a function, i.e. periodic function of atomic number. So it's periodic function, very important. The two words together, remember, periodic and then function has to do with properties. So hence the atomic number is very indicative of periodic function, and the function tells us a lot about our physical and chemical properties of that particular element. So we say we should recall that the number of electrons is equal to the atomic number of the element. Not necessarily. The number of protons is more accurately the atomic number of the element. So properties to be considered in this periodic trend are your atomic radius, which is the radius of the atom, ionic radius, which is the radius, ionic radius, which is the radius of the ions, and then the ionization energy, the energy that is required to ionize, and then electronegativity, ability to draw electrons from himself to form a covalent bond. So I just defined them very quickly from just their names, not anything. The definitions come naturally. Some of you cram it, but just understand it and you'll be able to explain it clearly to someone. So we're going to look at first on the list, which is your atomic radius. So your atomic radius can be defined and measured, assuming the atom is a sphere, because the way you can do radius is when things either circular or sphere. You can't do radius effectively with a square. Yeah, with a triangle or with a box, you struggle to do radius effectively. You can do radius on a plane or on a sphere. So the trend in the radius of the atom, so it decreases across the period and increases down the group. Across the period, down the group. That is how it trends. So it decreases like this, and increases like this. And why does it do that? Notice that going like this, you have more electrons. Going down, you have much more electrons. So hence you have atoms with wider and more bigger orbitals. So an element like hydrogen have a small radius, and then when you go down, you see more. You get down to even helium, you get down to neon, and all of those at the other end. Notice that now beat hydrogen to radius with larger radius. Then when you're going down, you know, the radius will definitely increase. So this is what we're talking about when we're talking about the radius in itself. So you have a diameter, which is one to another, then you have the radius. Don't know if you guys can see it effectively. This is that of the radius of one element and the radius of another, which is very different. You have, I think, that of copper here. I think this is chlorine. Of copper, and then this is chlorine. So you have a big difference between the radius, and the radius is the diameter. You notice that they use the center to the end, as of the center to the end, and when you divide that by 2, you have the radius, because the radius is, the diameter is 2 of the radius. It's 2 radius, it makes up the diameter. So the trends in atomic radius. So the increase in the radius is due to the screening of the electrons from the positive charge on the nucleus in the outer shell by the inner electron. So you have several electrons. So notice from this place you have these are your atoms. These are your atoms, and then you have this between. So what has been said here is, you know, you have several electrons and you have them laying on themselves according to the level that they are. So when you have the outermost, you'll probably have a bigger radius because you have much more electrons, and the lesser the electrons, the lesser the radius is going to be. So decrease in radius is due to the addition of electrons in the same principal energy level, and also the absence of the screening effect. The idea of screening is the layering or the covering of one on the other, because you have more and more orbitals on laying down the cell. So there's a screen has been created around about on those planes. So hence you have that line or layer around that forms the sphere. So the 10 core electrons are expected to shield the outer electrons from the nucleus. So notice that those 10 core electrons, when we say 10, with the 2 of the S and then the 2 of the P, and then the 2 of the 1s, 2 of the 2s, and 6 of the P is what makes that 10 core electrons. So that's what we call your effective nuclear charge. And if the word effective means is a solid or a good nuclear charge. The word nuclear has to do with the nucleus, and then charge is the charge that's emanating from the nucleus. So because ask yourself, why is the nucleus having a charge? Because it has a proton. This is that the neutron doesn't have a charge. So the proton is the charge is generated from the proton, and hence that charge is what results in the stability of the integrity of the atom. And hence the more electrons you have, the more it tends to balance off and then keep the same way the solar system is. You have the sun, which is at the core, bigger than the other planets going around about it, but the sun is there, tends to hold the other planets in place. The same idea. So it's like the solar energy, the energy from the sun. So it's effective solar energy. If I was to look at the planets to analyze or to explain what your effective nuclear charge is, very important that you tend to compare these things. Don't confuse yourself by them, but just compare them and better understand so that you can grasp. Because things you can't see are difficult to understand, but the things that you can see are appreciable or understandable in a sense. It's like somebody talking about telephone networks. You only know it as a phone, you don't know it as in network because you can't see it. You only know the offices as a company, a place you can see, but you don't know that the company is useless without that thing, that wave that hits your phone, that ensures that you can be able to hear someone speak from a long distance and reply back to that person. I don't know whether that makes what I'm saying makes sense, but I think some of us get the point. So the effective nuclear charge increases on the basis of that further extension or shielding. So we have the ionic radius. So positive ions are smaller than the atoms from which they form. Simply put, we know we have your positive ions, which are your cations, and the negative ones, which are your anions. So fewer electrons means increased effective nuclear charge on those that remain. So notice that when you have less electron, it means that the proton will be much more powerful than the electrons roaming around. Hence, there's a sense of control, the effective control, because of the effective nuclear charge generated by the nucleus. So negative ions are larger than the atoms from which they are formed. Negative ions are larger than the atoms from which they form. So more electrons means that there is more electron repulsion. So the size of the ion increases relative to that of the atom. So notice in the case where you have more electrons or negative ions, you tend to have repulsion because the electrons will repel themselves. Electrons will repel themselves. We know that a bar of magnet that has a north pole and a south pole, if you put the north pole on the south pole, there will be attraction. If you put the north pole on the north pole, there will be repulsion. So also the electrons will repel themselves because the electrons are moving and they are avoiding collision. And this is also the same thing in space. Notice that the Earth is moving in its own orbital. The moon is moving in its own. The other planets, Mars, Venus, and others, they are moving their own. There's no collision because they are moving their own, and it's amazing if you think about it or think about it deeply. So notice that this is also a repulsion if they are too much. So the size of the ion increases because of the repulsion. There's kind of like an expansion or an increase to compensate for the repulsion that's happening around. So this is what the comparison will look like between the atomic and the ionic radius on the group, on the main periodic table, the trend. Remember we said for atomic radius you have a decrease across the period and an increase down the group, and then for the ionic radius or radar, notice that radius, radar, singular, plural. It will be the same way with quantum and quanta, microbacteria, bacterium, same idea, singular and plural. So instance this on this, it's kind of increases this way and kind of similar, basically similar. It does the same thing this way and then increases down. Yeah, same trend. So we now look at ionization energy. So it's the measure of difficulty in removing an electron from a gaseous atom just to form an ion. So the idea is ionization is anything that has zation. It's almost like it has to do with the process. And when they say ionization energy, it's that energy that's required to form an ion. That's just in simple terms. It can be complicated to some people, just a measure of the ability of removing an electron from a gaseous atom. The M there is just a symbol of a gaseous atom. I don't think there's any element that has M, but just think of it as an element denoted M. So just to remove the electrons from that and make it form an ion is your ionization energy, because you need energy to produce that result. So the ionization, it increases across the periodic table from the left to the right, and then decreases down a family from the top to the bottom. So notice that this is kind of different. Increases like this, decreases like this. That's different from the previous that we looked at. So the ionization energy and atomic radius are inversely correlated to the other. So it means that one is opposite from the other, simple terms. So the smaller the atom, the more tighter its electrons are held to the positively charged nucleus. So that's for that. So hence this is what it looks like. So remember, ion is 26. When it loses 2, you have this. When it loses 3 electrons, you have this. So remember, we talked about the size with regards to the it's ion now. So yes, ions. We got with ionic radius. We said once you have electrons, when you have more electrons, you have it wider. Once you have less electrons, it will be smaller because you have effectively nuclear charge. The nuclear charge will be more effective, hence it will be pulling it closer to himself. But once you have many electrons that are around, there will be repulsion, and then to be wider. So you have this situation. Notice that it becomes smaller here, and it's more smaller here, because when you lose 2, see the size. When you lose 3, it becomes a little bit smaller. I hope it's making sense. So with that in mind, we had said that you have a decrease in this direction and increase in this direction. So now we're tackling the last one, which is your electronegativity. And we say this is the ability or intrinsic ability. It's not there, but intrinsic ability of an atom to attract electrons to the self to form a covalent bond. Notice that we talk about electronegativity with covalent bond, because remember, I told us that ionic bonds are formed metals, non-metals. Covalent bonds are basically formed with non-metals. And notice that the side for the non-metals are where all the negatives are. Chlorine, carbon, all of the things that are around the axis with p orbitals. So notice that all of them are around our axis, and what they tend to do is to share with one another. That's the covalent bond. So, and the sharing is the ability now to attract those electrons to yourself to share. So when I talked about the sharing, I said, look, there are some people that are very they always want to share stuff. So those people they are more convincing, so they can convince you to come and share with them. If they don't confuse you with their words, they can confuse you and convince you with their size. If the person looks intimidating, you'll be forced to share. I say this, some people can relate, but some people cannot relate. But the people that can relate will smile. So as electronegativity increases, the formation of an anion becomes more likely. So you always will have that formation of an ion when there's an increased electronegativity, because once, take for example sodium hydroxide or just a hydroxide ion, when oxygen pulls hydrogen to itself, you have that OH minus. Many others you can think of when you see that sharing. So there's a very likelihood of an anion formation. So the trends now for this is electronegativity increases across the period and decreases down the group. Notice that this is similar to ionization energy, because there's increasing across, unlike atomic radius and ionic radius that does reduce or decrease across the period and increase down the group. So fluorine is the most electronegative, has an electronegativity of 4.0, and then cesium is the least electronegative. I think it's 0.2 or something like that, like a 0.8 by fluorine is correct, 4.0. And if you see 4.0 and 0.8, that should remind you of your CGPA. Please try as much as possible to have a fluorine kind of CGPA and not a cesium kind of CGPA. Just a little joke there. So you notice that the increase is like this, and then the decrease is downwards. It's very apparent from what we see here. So that's it for the electronegativity and the values of the electronegativity. So we're done for the course. Notice that we have looked at what the quantum numbers are from the part 1. We saw how we derive the electron capacities of the energy levels, all in part 1. And I think we looked at the electron configuration, and then how to write some of this in part 1, and we talked about in part 2. And then we saw the orbital, how to draw the orbital, or what the orbital looks like, and then the electron atoms and then ions. Then we saw lastly now your trends, periodic trends, which are your ionic radius, atomic radius, the ionization energy, and electronegativity. And all of those things are what we looked at in your electron structure in the periodic table and the periodic table. So that's it for the lecture, and see you guys in the next chapter. And do well to study, do well to abreast yourself with what's happening. Check the announcement sections for announcement. Look out for the things that are happening, and look out for the quizzes or the assignments that are going to be available for you to do. And you have a great semester. So take care and see you in the next lecture.